Many times when considering processes modeled by functions or equations, we would like to essentially undo the application or composition of a function. In other words, given the output value of a certain function f, we would like to determine the corresponding input value. To this end, we introduce the notion of the inverse function. For a function f with domain D and range R, we say that the function g is its inverse if it has domain R and range D. And if we give g the input value f of x, then we get as output value simply x. Note that if g is the inverse of f, then f is also the inverse of g. If a function f has an inverse, then the inverse is unique, and so we denote it by f with a superscript -1. We say this as f inverse. In terms of compositions of functions, we find that the inverse is defined by the relations that f inverse of f of x equals x and f of f inverse of x equals x. For instance, if f is the function given by the formula f of x equals 3x plus 5, then f inverse is the function given by the formula 1/3 times the quantity x minus 5. Indeed, we may check that the composition f inverse then f and the composition f then f inverse satisfy the condition mentioned above. Another example is if we consider the function f given by the formula square root of x. The inverse in this case is the function f inverse given by the formula x squared. Note, however, that since the range of the square root is all non-negative numbers, we also need that the domain of the inverse is only the non-negative numbers, even though the maximal domain corresponding to the formula x squared is actually larger. We see again that the compositions f then f inverse and f inverse then f satisfy the conditions mentioned earlier. Note that since we restricted the domain of the square, we are indeed assured that f of f inverse gives back x and not minus x. Indeed, if we had allowed the domain of x squared to include negative numbers, like -3, then f applied to f inverse of -3 would equal 3, which is not equal to -3. So we see that for those conditions to hold, we really need the domain of the inverse to equal the range of the original function, even if that is not the maximal domain. This leads to an interesting question, however. Suppose we consider the function f given by the formula x squared on its maximal domain, i.e. all real numbers. Then we know that the square root is not its inverse, since the inverse of the square root is given by the square with a restricted domain. In particular, we showed that the square root of the square of -3 does not equal -3. We could perhaps consider the negative square root, but this would have a similar problem, since the negative square root of the square of 3 equals -3, and not 3. In particular, the inverse of the negative square root is the square with its domain restricted to the non-positive numbers. So we see that the square in its maximal domain has two different inverses when we restrict it to two parts of its maximal domain, but no inverse on the whole maximal domain. In fact, not every function admits an inverse. For instance, we see that the square on its maximal domain does not. We call a function that does admit an inverse invertible. A function is invertible when each distinct input provides a distinct output. Indeed, this is necessary if you want to determine the input solely from the output. The problem with the square on its maximal domain is that -x and x are distinct numbers for x not equal to 0, but -x squared and x squared are the same number. This definition of invertibility can be a bit tough to work with. In many cases, we can exploit the graph of a function to determine when it is invertible. The horizontal line test allows us to determine whether a function is invertible from the graph. It works similar to the vertical line test to determine whether a curve is the graph of a function. If every horizontal line intersects the graph in one or less points, then the function is invertible. And if any horizontal line intersects the graph in more than one point, then the function is not invertible, or at least not invertible over the current domain. For instance, we see that many horizontal lines intersect the graph of the square over its maximal domain in 2 points, which implies it is not invertible. So no inverse exists for the square over its maximal domain. However, if we restrict the square to either non-negative or non-positive numbers, then horizontal lines only intersect the graph in at most 1 point, implying that these functions are invertible. Indeed, we know that the square root and the negative square root respectively are the inverses of these functions. Now suppose we know that a function is invertible. Then how do we find the inverse? We will get to a method to find this using the formula after this video, but if we stick with graphs for the moment, it turns out there's a very simple method to determine the graph of the inverse simply from the graph of the function. Namely, if we consider the graph of an invertible function and simply mirror it in the line x equals y, we obtain the graph of the inverse, as exemplified here with the function e to the power of x, which is invertible with inverse natural logarithm of x. This method works because mirroring in the line x equals y means that if the graph of our invertible function consists of points x, y, the mirrored graph consists of points y, x. Now, since the graph consists of the points x, f of x, this means the mirrored graph consists of points f of x, x. So the mirrored graph is the graph of a function that provides the output x for the input f of x, which is exactly what we want the inverse function to do. Of course, a formula is often more useful than just a graph. So please proceed below to find out how to obtain a formula for the inverse of an invertible function from its formula.